But one thing in this context what we discussed, that so far we are transforming the variable by their first difference. That means we are the FD transformation is the basic base of this dynamic panel data estimation. First we take the first difference and then we are using instrument. So, first difference means yi t minus yi t minus 1 equals to rho yi t minus 1 minus yi t minus 2 plus beta xi t minus xi t minus 1 plus vi t minus vi t minus 1. This is the first difference transformation. But this first difference transformation, it has a major drawback, a major problem. What is the problem? Problem is, if we have any observation missing, then it will magnify the gap. Suppose any yit is missing, then for that delta yit minus 1 as well as delta yit plus 1, nothing is available. So, the major problem of first difference transformation is that magnifies the gap in case of missing observations. Okay, as in the case of unbalanced panel. So, if the panel is balanced, then it is fine, but when the panel is unbalanced, which is quite likely when you are working with large firm level data or large individual level data, there is no guarantee that all the observation would be available in all the periods. So, it is quite common that some of your observation will be missing, and if yit is missing, then delta yit plus 1, delta yit minus 1, all these observations are not available. So, it will magnify the gap, you will lose lot of information in case of unbalanced panel if you apply first difference. So, to overcome this, another transformation was suggested in the literature. That means, what is the solution? The solution was suggested as FOD, future orthogonal deviation, future or forward orthogonal deviation. Which is FOD deviation. What it does actually, instead of subtracting yit minus yit minus 1, it subtracts the average of all available future observations, right? Average of all future observations of yit. So, then that average can be calculated for any period, right. So, that means average can always be calculated even if you have missing observations. So, irrespective of whatever gaps you have in the data, sample average can always be calculated, and then what we will do, we will take FOD, and FOD transformation is available for each period except the last one. So, that means we can minimize the loss in data to a large extent if we go by FOD transformation in case of unbalanced panel. If the panel is balanced, then both FD and FOD will produce same result and our FD transformation will work. So, please keep in mind very carefully that whenever you are dealing with unbalanced panel, automatically we should not go by the FD transformation. We must use FOD, forward orthogonal deviation, to be used in that situation, and we have already demonstrated how to get FOD transformation, which is very easy to get in Stata, that using that orthogonal sub command after your XDA bond, right. So, this thing we have to keep in mind, that whenever we have unbalanced panel, then we will go by this, right. So far then we have discussed up to Arellano-Bond 1991 model, wherein we are transforming the equation by first difference, and then we are using instruments as YIT minus 2, and then we are estimating the model. And that estimation is called, so that means Arellano and Bond (1991), when you are taking the first difference and then using YIT minus 2 as IV, then that is basically called the difference GMM. Difference GMM. Okay. But what we have mentioned, that when your equation is in transform, that means we got this equation. I will write the equation once again for your understanding. YIT equals to rho YI T minus 1 plus beta XIT plus AI plus VIT. Then first we are taking the transformation YIT minus YI T minus 1 equals to rho YI T minus 1 minus YI T minus 2 plus beta XIT minus XI T minus 1 plus VIT minus VI T minus 1, and we are using instrument as YIT minus 2, assuming there is no presence of AR2, autocorrelation of order 2 or higher. Now, it is proved that when you are using YIT minus 2, that means lag of level, as instrument for delta YIT minus 1, a variable which is in differenced form, then that acts as a poor instrument. So, YIT minus 2 is a poor IV for delta YIT minus 1, and it becomes even poor when the variable follow random walk. So, YIT minus 2 is a poor proxy for delta YIT minus 1. Then what is the solution? Solution was given by Arellano and Bower. Arellano and Bower 1995, and Blundell and Bond and Bond 1998. What is the suggestion they had given? They said use YIT minus 2 as well as delta YIT minus 2. So, that means they are asking that you consider both level as well as the first difference as a system of equation. That is what they said. You use both of these as a system of equation. And then use YIT minus 2 as an instrument for the first difference variable, at the same time delta YIT minus 2 as the instrument for the level. Okay. So, YIT minus 2, they said in this system of equation YIT minus 2 is IV for differential equation and delta YIT minus 2 is IV for the level equation. So, both level and first difference are used, and when that is the case, then the model is known as system GMM. System GMM. Okay. We are using both level and first difference equation and we estimate the model. And in Stata, we have demonstrated how to estimate a system GMM. When it is a difference GMM, we need to specifically mention that we do not need any level equation, no level equation, while when you go for system GMM, we need to remove that no level equation sub command, so that Stata will understand we need both level and the difference form of the equation. So, we are considering a system of equation, that is what they said. But in this way, when you are estimating both difference and system GMM models, one disadvantage is that we are creating too many instruments. We are creating too many instruments, right? And then when you have too many instruments, so the problem of this problem of GMM estimation too many instruments. And when you have too many instruments, that means over identifying restrictions should be valid for each IV. One advantage of this GMM estimation is that it corrects endogeneity by using instruments from the system itself. That means we are taking only lag of YIT. We are not looking for instruments from outside. And when your instruments are coming from within the model, then one thing is guaranteed, that they are highly correlated with the endogenous variable here YIT minus 1, minus yit minus 2. So, that part is guaranteed. They are all highly correlated with the endogenous variable. But the next criteria, the second criteria that we need for any instruments to be valid is that they should not be correlated with the error term, right. When you have too many instruments, then the problem is that how do you know whether over identifying restrictions are valid for each and every instruments. That is the major disadvantage of this GMM estimation technique. That is the reason when we estimate the model, what we can do, we can actually control the number of instruments to be used by using collapse command or by specifying the lag length within the GMM style instrument, right. So, that is one thing we need to be careful. So, that means we can limit the number of instruments IVs by restricting the lag of yi t minus 1 within the GMM style IV. So, in stata we used to specify GMM, as you know, then within the bracket if we put let us say L dot N1, simply this one, that means I am not specifying any lag length, it will take whatever lag is available, but we can specify the number of lag here, right. We can specify the number of lag here, so that stata will consider only this many lag to be used for the estimation technique, right. So, by restricting the lag also we can actually improve the quality of the estimate. Sometimes you can see that your estimates are not lying within the interval, then by restricting the lag you can improve the quality, and sometimes you can see that it can lead to your estimates lying very well within the interval, right. That is also you can do it. Then there are two variants of GMM actually. GMM estimation are of two types. One is one step and another one is two step, we have discussed. Basically, in two step you see when you go back to the expression what we have derived, that beta 1 hat is appearing within the expression of beta 2 hat. So, that means this is beta 1 hat and it is actually this beta 2 hat, which is actually a function of beta 1 hat. If you go back and look the expression, you can see. So, two step GMM is actually more consistent, but what happens to two step either difference or system GMM, that the asymptotic standard error asymptotic standard errors are severely downward bias. So, whenever we are using two-step GMM, this point we have to keep in mind that the asymptotic standard error of this beta 2 hat, they are severely downward bias, and we need to apply Windmeijer correction. So, what is the solution then when you are using two-step? So, solution is we need to go for Windmeijer 2005, the correction that we have discussed. It corrects for the standard error. Otherwise, it will fall drastically if we do not correct for Windmeijer correction when you are using two-step either difference or system GMM, right. So, how do you do that Windmeijer correction? When you are estimating the model using xt upon or xt upon 2, then basically what we are doing, that two-step GMM estimates are theoretically robust. Then what we need to put, two-step, within the two-step, two-step GMM, put robust. This we have to put. Two-step GMM, even if we do not put, then they are already theoretically more robust than one step, but when I am putting robust again within the two-step, right, that means I am asking for Windmeijer correction. Okay. So, xt upon 2, and then if you put two-step after all this command and then put robust, then it will lead to Windmeijer correction. Okay, Windmeijer correction. So, that is also something we need to keep in mind. So, these are all the basically in summary about the theoretical things that we have discussed. Now, when you come to empirical estimation, then it can be estimated using either xt abound command, or we can also use xt abound 2 developed by David Rudman. So, all our discussion in this system GMM is mostly based on David Rudman's fantastic article on how to use xt upon 2. So, you can look at the reference, a fantastic reference, how to do xt upon 2 by David Rudman. Okay. Now, if we apply xt abound, then the post estimation checkups we need to do it manually. So, after xt abound, again you need to put air test, then what is the number of lag that you need to specify, and then you need to also put the over identifying restrictions, so on and so forth. Also, xt abound can estimate only difference GMM. So, system GMM cannot be estimated by this xt_abond to xt_abond command. We need to specify, if you recall, xt_dpd_sys. So, it can estimate only difference GMM. Secondly, post estimation checkups should be performed manually. Post estimation checkup means I am talking about autocorrelation. AR2 should not be there, AR1 should be there, and over identifying restrictions whether they are valid or not, right. But when we do xt_abond2, the advantage of xt_abond2 is that, first of all, xt_abond2 can estimate both difference as well as system GMM. As well as system. Secondly, test of autocorrelation that means AR1 and AR2, AR1 should be there and AR2 should not be there. Test of autocorrelation and over identifying restrictions are inbuilt. So, we do not have to again go for this. Thirdly, can implement or can perform windmeijer correction. Okay, after two-step GMM with that robust command. So, these are the advantages of xt_abond2 over xt_abond. Okay. This xt_abond2 developed by David Rudman, this can perform these interesting features. It can estimate both difference and system GMM. It test of autocorrelation and over identification, they are inbuilt, and it can perform the windmeijer correction also, which is required when we are applying two-step system or difference GMM, because the standard error, asymptotic standard error are downward bias, right. So, these are the things we need to keep in mind, that it is better to use xt_abond2. Okay. Then one more important point, using time dummies for GMM estimation. See, what we assume in this GMM estimation technique suggested by this Arlan-1 bond, that there can be autocorrelation and heteroscedasticity within individual, but no autocorrelation across individual. So, they assumed no autocorrelation across individuals. And this mostly holds good when year dummies or time dummies are included. Using that year command. So, if we use YR star, then it can include the year dummies. Now, what is happening here? If you recall, we have discussed how to purge fixed effect in the model. AI was creating problems. What we did? We created individual specific dummies in the model and said we can actually estimate LSDV, wherein we are assuming that all the individuals, they have a different intercept. So, individual specific intercept as a form of dummy we introduced in the model to take care of that AI factor. Same logic is applicable when we have year dummies, then the assumptions that there should not be autocorrelation across individuals over a period of time, that assumption is mostly true when you have year dummies. So, when you are estimating a difference or system GMM, do not forget to include time dummies in the model, right. So, these are all the things we have to keep in mind, that xt upon 2 mostly we will be using, and then when you are using xt upon 2 after estimation, no need of checking the post estimation checkups, because those are actually inbuilt in my model, right. So, this is how we can estimate the dynamic panel data model using the xt upon 2 command. Okay. Now, we will quickly take one data set. We have already demonstrated several estimation. Since we are summarizing, I thought of summarizing even couple of models also. So, this is again that Arellano-Bonds original data xt. If you put we use AV data, you will get the information. Here our objective is to estimate the determinants of labor employment, and employment is actually a factor of previous year's employment, wage, capital, lag of capital, output, industrial output, and then the lag of it, that is all. So, before you estimate, please do not forget to get your limits by using OLS and FE. Once you get the limit, then you start with xt upon 2. So, this is xt upon 2. Okay, xt upon 2, and then I have my dependent variable in, all right, and then what I will do, I will put NL1. So, NL1 is here, and then I can put NL2, then I will take wage, I will take wage, and then wage of lag 1, capital of lag 1, and capital of lag 2. This is how you can use, and then we can take YS L1, YS L2, and then we need to put the year dummies as I mentioned earlier. So, this is the equation we have specified, this is the model we have estimated, and now second part of the command is basically all about how you are specifying instruments, which variable you are considering as endogenous, that will come in the GMM style, which variable you are considering as predetermined and exogenous, that will come in the standard IV style. So, within the GMM style, what I am assuming that only NL1 is my endogenous variable, and I am now specifying the lag also. So, I will not take whatever lag is available, rather I will take only fifth, right. So, this is GMM style, and then I will put all my IV style instrument here. Those are W, and then WL1, then capital, then capital L1, and then I have capital KL2, and then I have YS, and YSL1, YSL1, YSL2, and then I have my ER also that will appear here. And then if we want to estimate difference GMM, as I mentioned, no level is required, and then we need robust, and then small sample correction. That means all my test statistics should be T, not in Z, right. We are assuming a small. So, this is basically the model you need to. So, first part of the XT-2 is this, which is your equation of interest. Second part is basically concentrating on how you are changing the, how you are deciding about your endogenous and predetermined variable. Sorry, I have made a mistake. I have not mentioned the lag over here. So, after NL1, here I have to put lag, otherwise data is not recognizing what is this 2 and 5, right. I need to specify lag. And then first thing what we need to do is to check whether number of instruments are actually less than number of groups, which is much less than 140, right. Then I will come to the second part, 0.83, whether it is lying within the interval or not, right. It is lying, but you in your context do not think that only 0.73 and 1.04 would be always the limit of your estimates. That is the limit used only for this data. So, when you will be working with your own problem with your own data, then please try to estimate that model ignoring the dynamism using FE and OLS, and you will get your new bounds that to be used actually. So, it is in this case, since we remember I am not estimating that, but one thing if I would remember that when we have estimated Anderson and Hessius model, then they were actually not coming within the limit, that also we have proved. So, here it is lying, and then my autocorrelation of order 2, which is basically but look, here is a problem that autocorrelation of order 1 is actually there. So, that means there is some problem in the data. So, maybe we have to recheck what is happening here. Okay, we need to recheck. So, there must be some problem. We can always rectify that by changing the IB style instrument to GMM style instrument, and we see. But anyway, this is an example I was talking about. So, your AR1, neither AR1 nor AR2 AR2 is actually there, AR1, this is what the opposite of what we actually want, and then Hansen test of over identifying restriction is satisfied. That is fine, that is fantastic. Okay, that is fine. So this we need to carefully recheck. My AR1 should not be there, right? Now the same equation, if we want to estimate using system GMM, then what we need to do is we need to simply remove the no level. That means I want level as well. Sorry, that means here again this lag I have to put, and then I have estimated once again. So coefficient is lying within the interval. This is one step system GMM. Number of coefficients also much lower than number of groups, but the same problem happening that both AR1 and AR2 are significant, which should not be the case, right? You need to, whenever you are getting this type of situation, then you have to be careful. Good that we are getting a situation like this. So in this particular data, whatever specification we have made, then one thing is that even though your estimates are lying within the interval, it is of no use, because AR2 is also significant. And when AR2 is significant, what we have mentioned, that our instruments are actually not valid. Okay. So this is, we have estimated one step system GMM. If we want to apply two step, then robust, here we need to put two step, then robust and small. So basically by putting two step and robust, I am estimating two step system GMM. At the same time, by putting robust command, as I mentioned, I am asking Stata to perform the windmeijer correction. But here what is happening, two step system GMM fail to put your estimates within the limit, but if you look at your AR2 is satisfied, right. So that means earlier we are getting the estimate within the interval, not the post estimation checkup. Now we are getting post estimation checkup, fantastic, but the other one, the estimate is not lying within the interval, right. So that means we need to again change the specification, and good that we are getting these situations. This will help you understand what are the other type of situations that may arise, right. We need to satisfy both the things. My estimate must lie within the limit, and my post estimation checkups also should be satisfied, but here it is not happening in that way, right. Since this is the case, so what we will do, what about our Hansen test of over identification? Hansen test of over identification is also satisfied. So probably we need to specify the command over here. So what we can do, we can put, we can actually use this W and capital also as GMM style instrument in this situation, right. So if you want to use that, then what you can do, we can put, let us say I am estimating this command xt upon 2, and then I am using n, I am using n, and then nl1, nl1, right. And let me take NL2 also. If you want, you can remove this NL2 and check whether that gives better result, and then W and WL1, and after that we can take K, KL1, KL2, and then YS, YSL1, YSL2, okay, YSL1, YSL2, and then we have to put that ER dummy, all right, and then comma GMM. Within the GMM, now I am putting NL1, WL1 and KL1 as instrument. So, that means now I am considering wage and capital also as instrument, and then within IV I will be using, within IV what I will use, YS, YSL1, YSL2 and YR star, then no level, robust and small. So, if we do that, then what is happening? My instrument, the coefficient is lying within the interval, my AR1 is satisfied, AR2 is not there, that is also satisfied, fantastic, and then Hansen test of over identification is also satisfied. So, that means one step difference GMM by considering the endogenous variable from only from Y to W and K has given me fantastic result, wherein both the situations, both the conditions are satisfied, right. So, that is why we said that we need to check actually which specification works better. So, there is no clear cut rule. So, we have two objectives in mind: estimate must lie within the interval, post estimation checkup of autocorrelation and over identifying restriction should be satisfied. So, that is achieved over here. Okay. So, with this now we are closing our discussion today. This is the last session of this applied econometrics, where we have summarized the theoretical estimation as well as theoretical background as well as empirical methods to estimate the model. We have seen several alternative versions of dynamic panel data estimation. You can play around with the data and you can ensure how the estimate will lie within the interval by playing around and specifying alternative models. So, with this we are closing the session. Since this is the last session, I wish you all the best for your learning on applied econometrics. In this econometrics, we have discussed advanced topics, but we could not cover the time series econometrics. Probably my next course will then be on time series econometrics. I wish you all the best. Happy learning of your applied econometrics. Thank you.